a very warm welcome to everyone on the call, and good morning, good afternoon, and good evening to all of you. And thank you ever so much for your interest, and we're hoping that this will be a series of webinars, and we actually called it even Thought Leadership, because we would like to invite some influential speakers and who's got vast experience and experts in their fields, and hopefully they'll come and share their stories and their success stories as well. And so I'm very honored and delighted to introduce Hazel Courteney. So she kindly invited my invitation to kick off these series, and she actually it was my fault. I wasn't very well planned, but I asked her to quick bio, and she sent me a CV, and probably it'll take me about 10-15 minutes for all the achievements that she
don't do that, Cengiz.
But very briefly, I think you know what is important is Hazel started her career in the industry to start with, Westland Helicopters, and then moved into CAA, UK Civil Aviation Authority, and worked in various different roles. And I think at some point she also worked in NATS as well. But before she left UKCAA, and she was the head of strategy and safety assurance. And since 2016, she's working as an aviation consultant for her own company. But certainly she's got some great achievements in terms of human factors, and going back to the early days of introduction in factors requirements in civil aircraft design, and certainly introduction of particularly the 251302 within the European framework, but it's also the harmonization with the other, for example, the FAA and so on. And if I'm not mistaken, I think Hazel chaired the first ICAO Annex 19 panel as well. Is that correct?
I did, yeah, 2 terms. So for the edition 1 and edition 2.
So there you go. Well, I mean, anything about safety management and SMS, and we can blame her. Right? I wouldn't envy her position to start with, because obviously it's a big challenge to trying to bring the aviation community together and actually trying to come up with some narrative that is going to be so influential throughout across the entire world. So, but obviously today's talk is also very much sort of almost 20-30 years story, if you like, that's starting from early 2000s, or if not even going back to 90s. But certainly not only the industry experience, but Hazel holds a Bachelor of Science in Psychology from Birmingham University, and Master of Science in Engineering Production, again from same university, but also Doctor of Philosophy, PhD on Aircraft Design Studies from London University. So I think, you know, she's, you know, who else is going to talk to us about this subject, but mainly focusing on the human hazard analysis, a methodology that is, in my view, and I don't want to sound critical, but not very well known all across the world, which I do believe that it should be certainly taken on board and actually used not only by a few manufacturers that she managed to convince, but almost across the industry by everyone. So without further ado, over to you, Hazel, to tell us the methods that you developed over the years, and also the story behind it, really.
Okay, thank you very much. So hello everyone. What I will do, if I may, is I'll talk a little bit about human factors generally for anyone that is new to it. And then I'll talk about what's happened in the cockpit, what's happened with aircraft maintenance, and speculate about what might happen next. Okay. So one of the issues in human factors in aviation is that every different discipline means something different by human factors. So the human has an interface with the aircraft design. We also have human factors in aircraft maintenance, what you might call hangar human factors. Operational flying talks about CRM, managing fatigue. Aircraft maintenance also talk about managing fatigue, managing the environment, so on. But what we're going to talk about today is the interface with the design specifically. And one thing we know is that if we have unrealistic expectations of people or anything, it can cause problems. No one would think about blaming the donkey for this, but sometimes we do overload people and give them a heck of a challenge and then kind of blame them when something goes wrong. So what we have in terms of creating a flight is that in order to fly, we not only need the aircraft and the mechanical parts, which are typically more reliable, but we also need a human pilot and a human maintainer. And without all three of those components, the flight's not going to happen. So in a total systems kind of view, we really need to make sure that all of those things are working well together in order to achieve our goal of a safe flight. Now, anyone who's ever used anything knows that the design of equipment will affect how easy it is to operate and maintain, how likely it is that you're going to make an error doing it, and what the consequences are of that error. So how easy is it to detect? How easy is it to detect that you've made an error, and what's the consequences for the system? And just to remind ourselves that a huge proportion of the actions that people do in aviation are correct and successful, and only a very tiny proportion are incorrect. But the consequences are so serious at times that we are looking for, really in some cases, very high reliability levels. And although we have lots of good practices that help us to reduce the likelihood of errors, we have our CRM, we have our fatigue management, we manage our environment, we have supervisors, we have duplicate inspections, we have all of those things. Sooner or later, someone will make an error if it's a foreseeable, simple type of error. So if it's so important, then we might want to think of other ways of containing it, and that might be through the design. So if the system allows an error to happen, the human error will at some point occur, whether we've made it very rare due to good management in the hangar or in the cockpit. Still, eventually, someone will do something wrong at some point. If the system then lacks error tolerance, that's when we can end up with an accident resulting. And I'm sure you're all familiar with the Swiss cheese kind of principle, where we keep trying to prevent losses at various stages, but if it goes all the way through and eventually, I always think it's a bit like calling every goal scored a goalkeeper error. When we talk about pilot error or maintainer error, they're just the person at the sharp end who is trying to prevent the bad thing happening. But all the rest of the team do have a role, and part of that team is the designers. So for me, the design engineers are some of the midfield players who are trying to stop anything, trying to enter the goal, if you like. And just one kind of airworthiness point, really. When we're doing in design safety calculations, it's always interesting that we quite often attribute 100% perfect performance to the human operator. And yet if we automate the function, we will then assign it an error rate. So if the part of the system that performs a function is human, we may say, well, we'll assume that's being done correctly in our safety assessment. But when we automate it, typically to make it more reliable, we then assign it an error rate and put that as part of the part of the safety calculations, which is a little bit incongruous to me. So perhaps that's something that we will address as we go forward. So what's been happening in terms of the cockpit human factors in design? Well, it all started here, 8th of January 1989, astonishingly. This was an accident that happened in Kegworth in England, where a 737 parked itself on the side of a motorway, largely because the pilot had shut down the wrong engine when he was having engine problems. And then he had 2 engine problems and it came down on the motorway. And although it's not actually cited in the accident report, there was a lot of criticism from the sort of rising discipline of human factors at that time, with people saying, well, there's human factors problems associated with this design. No wonder somebody would make an error. And that criticism was not very well received, as you can imagine, by either Boeing or the test pilot community, who were saying, well, you know, it's very clever to be wise in hindsight, but you show us how to do better. Anyway, because of all of that, the Civil Aviation Authority in the UK said, you know, we're getting all this criticism from these human factors people publishing papers and so on. We probably need one of our own, and a post was created, and I went and took that post. And there was a lot of challenges around human factors at that time. We were taking people from a background that typically wasn't design engineering. So as human factors people started to come into the industry, there was really an issue about learning to fit in, because what would happen if you're in a design office, the stress engineers will say your design needs to be at least this strong. They won't say it needs to be as strong as possible. They'll say it needs to be as strong as this. The weights engineers will say it mustn't weigh any more than that. They won't say it needs to be as light as possible, but they'll tell you, you know, that there's a maximum weight you must achieve. But as human factors people came in, they were doing what they'd been taught in college, which was to say it must have the best human factors possible. And it's a little bit like, you know, the spoilt child in the room. No, I can't settle for anything other than everything being optimized for me, kind of thing. So there was a little bit of difficulty in fitting that in to the design process. And there was something around the human factors of human factors, because human factors in design is all about making things good for the user, making it optimized for the purpose of the user. And, you know, and I'll include myself in this. We weren't terribly good at putting things in a form that was useful to the design engineers using it. So we would say, well, design A is better than design B. Yeah, well, design A is also 10 times more expensive than design B. So is design B good enough? And of course, the discipline hadn't really developed enough to draw the line in the sand and say what is good enough at that time. So you would get people who looked a little bit like the chap on the right, getting quite irate about what was happening. And that's no surprise. There's also the issue about how to specify in advance of a design from a regulator's point of view what something has to achieve. We had to accept that, you know, the world of aviation already exists, so something might be the best design from a ergonomic or human factors point of view, but if it's different from everything else that's already in existence, you have a standardization problem, and people having to then maybe transfer from one kind of primary flight instrumentation to another, which creates its own risks. But the biggest problem of all was specifying really how much is enough. And this is one of the problems that we've tried to address going forward with human hazard analysis. And then in terms of regulating it, there was a lot of discussion about whether you regulate the process by which something's developed. In other words, have you consulted enough pilots? Has someone got Has someone got a live microphone? Thank you. Do you specify the process they have to go through and say, well, you've got to do simulator trials, you've got to use at least 10 test pilots or line pilots or whatever? Or do you specify the characteristics of the product? And that will just be the judgment of a small number of people, typically test pilots. And what we concluded in the end was that you have to specify the product, because as we started to work with the industry, people would go through a process and then magically come up with whatever design they wanted to do in the first place. So you would have quite different conclusions apparently coming out of quite similar processes. So we gradually went for the product. Anyway, after trialing it on many different products as we developed it, and then creating a policy for Europe, and then going through harmonization with the FAA as well, what we ended up coming up with was this paragraph, which is 1302 in the design codes. That came in 2007. I won't read through it all, but basically the equipment's got to allow the accomplishment of the tasks that are set to the pilot. It's got to be clear and unambiguous, accessible and usable, and the effects on the aeroplane or systems has got to be very clear. System behaviour has got to be predictable and unambiguous, and enable the flight crew to intervene when they need to. All of those really are developed through assessment, scenario-based assessment and pilot feedback. And then finally, there's the effects of error. So the installed equipment must enable the flight crew to manage errors resulting from the kind of interactions that can be reasonably expected in service. And you'll see there at the end, this does not apply to skill-related errors associated with manual control of the aeroplane. The reason that got in there was because certain manufacturers at that time were saying, well, if I suddenly pitch forward to the maximum extent and fly at the ground, that's an error. You can't design an aircraft that stops me doing that. And of course you can't. So this particular clause was added to just avoid trying to attribute interesting flying inputs from getting into this analysis. So it's the last one that really requires the error analysis. Most recently, this has come into the helicopter design code, CS 25 and 27, last month, which is very interesting for me. I'm doing some work with Volocopter at the moment, so that means I'm going to be subjected to my to the requirements I helped start. So there you are. They say no good deed goes unpunished, so I'm going to have to try to comply with those on behalf of Volocopter shortly. Okay, so the main issue that we wanted to talk about, aircraft maintenance. So a lot of the human factors in aviation has been aimed at the cockpit and pilots, but aircraft maintenance is also very key, obviously, in making sure that we don't have in-flight technical problems. And errors in maintenance have been primary causes in fatal accidents. They've also been responsible for some of the contributory factors. So if, for example, an engine malfunctions and the pilot doesn't successfully handle it, typically that will be recorded as a pilot error because it's deemed that if it was a controllable fault or a controllable situation, then they should have handled it. But had the engine not malfunctioned, the situation wouldn't have arisen. So I think aircraft maintenance is something that probably is more prominent in safety than is obvious from the accident statistics, maybe. So at one point, we started to put together a proposed requirement for the whole aircraft. And I don't have a copy of it today, unfortunately, but the the proposed requirement, which never got adopted, was something along the lines that a single foreseeable human error during operation, maintenance or production should not be capable of leading to a catastrophic loss. So in order to develop a means of compliance for a rule like that, we had to sit down and scratch our heads and say, okay, what could a good means of compliance look like? Well, first of all, it has to make sense to design engineers. It's got to fit into the design engineering process. It's no good being a completely separate kind of approach. It's got to be systematic and documented. It's definitely got to be affordable and contained. It can't be a kind of blank check type of approach, that's too big and unaffordable. It mustn't need a human factors PhD to be able to apply it. Whatever method we used has got to be something that all of our engineers can apply. It's got to be able to show how much human factors is enough, so we can draw the line in the sand and say, when are we done? When are we actually finished? We can't just go on making things better and better and optimizing everything. And what we really need is a common standard to apply to all designs. So if we want to be able to say we've applied human factors to this, it should be one common standard. So this was a problem that I was kind of scratching my head over in probably the late 1990s. And to try and get something that fitted in with the general design process, I thought, well, let's look at what the design process really is. What are the bones of it? So something that we do in all design processes, we identify how components could fail and how you would know, how you would detect that failure. We assess the safety impact of component failure in service, and then we ensure that the reliability of the component that we achieve is commensurate with the safety impact of a failure, which is all good common sense stuff. But what we don't always do is a kind of parallel process for human error. We don't systematically identify how tasks can involve human error and how that would be detected, assess the safety impact of human error in service, or ensure the degree of error tolerance is commensurate with the safety impact of the error. So for me, it's a parallel thought process that we are applying to a function of the total system, whether it's done by the technology or whether it's done by the human. It's still got to be done and it's still got to work. And as I said in the beginning, if we automated it, we would soon go through those steps. So why not be going through them when it's a human doing it? So I started to think about how can we develop a kind of parallel tool. For the technical systems, we've got a specification in the System Safety Assessment Targets in 25.13.09, for those of you that are familiar with those design codes. And the regulation that we had drafted, although it, as I say, it never got adopted, but you never know, it still might, was looking to specify a target as well. In this particular case, to protect safety from single foreseeable errors. So how would we do that? Well, you can use the existing tools like the functional hazard analysis and fault tree analysis to identify where are the critical functions that might happen. And we can augment the functional hazard analysis and fault tree analysis to add the potential for human error into those well-trodden techniques. And in fact, that's something that we're doing at the moment on a live project. The design assessment identifies critical parts, so we can equally identify the critical human tasks on those critical parts. So we're not looking to apply this to every single maintenance task on an aircraft, or even every single maintenance task on critical parts, but just the critical tasks on the critical parts. Although you could identify it any way you wanted to. You could say, well, on all rotating assemblies, I want to do all the human maintenance tasks if you wanted to. Depends how much time and effort you want to invest in it. And then just as we apply a failure modes and effects analysis, which will ask ourselves those questions from a technical point of view. How could this component fail? You know, what are the ways it can fail? When would we find out? What are the safety consequences and all those other questions? So we can do a human error modes and effects analysis, or a HEMIA, which we can conduct in parallel. And some, you know, people have sometimes raised various objections to doing a sort of human process. Some people will say, well, hang on a minute, that's a human is outside of my aircraft, so I don't need to take account of it. But we already take account of bird strikes, for example. We already take account of weather conditions. We probably don't want to build an aircraft that can't deal with wind or rain, or, you know, or bird strike. So we already do that. Some people will just shrug and say, well, that's just human error. You can't do anything about that. But, you know, we know that you can do something about that. You can most certainly reduce the likelihood by good, clear design, but you can also reduce the impact of it. So by redundancy, or by gross error checks, or by protected switches, or by parts that won't fit the wrong way round, by flags. There's all kinds of ways of reducing that, or by sealed unit. You know, if it's that higher risk, by sealed units that don't require a human action on them or a human maintenance. So it can sort of bring out a bit of a initial reaction in some people in the engineering world who will say, well, hang on, you know, this is nothing to do with me. But actually, I think if we're going to look at something as a total system, then we need it to be addressed. So the general kind of human hazard analysis process is three stages, really. First of all, you select the tasks. We've proposed the critical tasks on critical parts using the aircraft level functional hazard analysis, functional hazard assessment, and fault tree analysis, which will help to select tasks. That's not the only way of selecting them, but that's something that has to be done in advance of applying the kind of human error modes and effects analysis. Analyze the tolerance. So what errors could occur? How would you know that you'd made an error, and what's the safety risk involved? And then mitigate it if needed, and that needs to be kind of proportionate to the consequences, the likelihood and the consequences of the error you're talking about. So if something is even reasonably likely, and if the consequence is really severe, then really the best option is design change. You know, something that either prevents you from doing the error, not makes it less likely, but actually prevents it, like parts that will only fit in one direction. If it's something that's less likely or much less serious, then you might be thinking about procedures or training if it's suitable, or documentation change. We've found a lot of things where people have said it's not that the documentation's wrong, it's just not that helpful. And if you want me to get this particular task right because it's really, really important, you could make it a lot more helpful than that to you know, make it more likely that I'm going to get this right. So when we were first thinking about this, we tried it on the back of the proverbial cigarette packet a few times, and it seemed to work, and then offered it out for postgraduate projects and things to apply to real systems. And it seemed workable, but there's a whole world of difference between doing that in an academic setting and doing it in an actual aircraft design team. So we got some research money within the CAA, and we offered research contracts out to 3 big manufacturers: Airbus Industries, Smiths Industries, and Rolls-Royce. And all 3 of them did good projects. They all used it and showed some benefit from it. And the project manager in Airbus, a young man called Simon Gill back then, said, well, you know, we've done this project, but I'm not just going to finish the project and file it and then do another project. So he developed it a bit further, and he developed it into the normal procedures within Airbus Industries, and it's been used on a number of their products. To my knowledge, I think the 380s got some elements of this, the 400M, I think the A350, to our knowledge. And it got worked into it just into the general procedures. So Airbus took that up, which was good, but at the time, not much else happened. And because the rule that had been proposed was not adopted, and I think, to be honest, I think the main reason it wasn't adopted is that EASA was just being formed, and there were a lot of priorities ahead of a new human factors rule back at that time. So it didn't get taken up, but nonetheless, you know, Airbus has been using it, so that demonstrates that it can work quite well in a proper project. So as time went on, I started doing a little bit of work with Heli Offshore. It's an international organisation for the offshore helicopter industry, and proposed to do something like this, or to raise this for the helicopter industry, because technical failures are much more prevalent in helicopter accidents than they are in fixed wing. I think, you know, something like 40% of accidents involve, or, you know, causal technical failures. And again, Airbus helicopters in particular really went with this idea and have applied it very much on the projects that they're doing. And we started to offer to run workshops with helicopter manufacturers and the maintenance organisations that maintain them, because in order to properly evaluate where errors could happen and what kind of errors could happen, the most fruitful way to do that is to bring the design engineers into the room to workshop it with the maintenance engineers that actually do that job in the front line. And particularly if you're doing it as a review of existing aircraft, you can be dealing with the maintenance engineers that do these jobs every day. So they know very well what kind of things are happening out on the line. So what's the general status of how maintenance engineers are seeing manuals and designs? This is a little bit of quite recent research. It's very similar to research that's been conducted in the past, but just to remind ourselves that it's still the case. This is been done in 2020. 36% considered manuals difficult to understand. 45% indicated that procedures lack detail. 57% that they routinely find technical errors in maintenance manuals. 82% knew the process to amend manuals, but the majority perceived it as long, difficult and frustrating. And 80% admitted using unapproved documentation and aid memoirs. So right up until now, we're still not giving a particularly good support to our maintenance engineers. So the general process then is systems and components are selected from the existing aircraft level analysis. High criticality maintenance tasks on those components are identified and may be further prioritised by questions or observations. Selected tasks are subjected to a human error modes and effects analysis by joint design and maintenance engineer teams, who will look at what kinds of errors might occur, what existing controls are there, so what's already in place to make errors less frequent or less serious, and what's the likely safety impact if an error is made. The safety threat is then assessed, and where necessary, an appropriate level of mitigation is proposed. Safety is then reassessed with the proposed mitigation in place, and if that's now an acceptable level of risk, the mitigation is recommended. So what kind of mitigations might that be? Can be improved documentation, less cross-referencing, colour photographs, very popular, clearer pass-fail criteria for inspections. That's something that we've heard a lot about. Improved instructions for special tooling. When we've done workshops on this, we've actually heard people say, you know, yeah, we've got that special tool, we don't know how to use it either. Supplying things as a kit of parts. There's been quite a number of accidents, particularly on rotorcraft, where self-locking nuts have been reused and reused. So they're not very self-locking anymore. So things like supplying things as kits of parts really help people to not do that. Parts that only fit one way, color coding, lids that won't close if you've fitted it incorrectly, shielding a component from damage when it's being removed, when things near it are being removed or installed, and system change for redundancy. If all else fails, it might be a cockpit alert to stop the pilot from taking off if something's not correctly fitted. So with the total system approach, the problem could be that we're expecting a level of reliability from human beings that's just unrealistic. So the problem could actually occur or manifest itself in the human. That doesn't mean they're the problem. It means that we've kind of, a bit like the donkey lifted into the air pulling the cart, we've expected something of them that is just not realistic about human beings. We are not perfectly 100% reliable in a world that requires us to be perfectly 100% reliable. But the solution may not be to keep trying to put more burden on the human. The solution could be to do something better in the aircraft design that relieves that burden a little bit. So we've had quite a number of workshops through Heli Offshore with Airbus helicopters, with Leonardo helicopters, with Sikorsky. Bell have come along. Heli One, we did a workshop in Norway with them. And at the workshops, we bring design engineers together with maintenance engineers and generally a couple of human factors facilitators. So you can see there, me at the front, I'm quite easy to spot. And my colleague Simon Gill, who was the gentleman who progressed the human hazard analysis at Airbus, I invited him to join in the Heli Offshore work so that we could run these together. And I've just, you're not intended to be able to read this, it's just an example of the format. You'll see at the top there, the human error modes and effects analysis. It's a kind of automated sheet. You see some green and yellow squares there. One of the manufacturers likes to narrow, sort of further narrow down the amount of tasks that they're addressing to prioritize them by asking a number of questions, such as, does it require special tooling? Does it require a lot of resources? Is access good? And so on. So that if those things score highly, then they prioritize that and put it to the top of the tree in terms of doing those things first if it's demanding, particularly if the documentation is not very good. And when we've gone through this process, you tend to find about 90% of the tasks just go through. Of the ones that we identify issues with, a majority of those result in documentation change, and it's only quite a small proportion that result in a recommendation for design change. So you're talking about, 10% of the 10% really. It's a very small number, but for those tasks where it is recommended, it's because you've got quite an easily foreseeable error that could result in a serious safety situation. And one of the things that people stress about a little bit with this is, what exactly do we mean by a foreseeable error? So you can't build an aircraft that's protected from any crazy, unlikely thing that any human being could do. But professional pilots and professional maintenance engineers don't do crazy, stupid things. They don't just do random actions. They're qualified professional people. But occasionally they do what we call foreseeable errors. And to kind of contain what those might be, foreseeable errors we count as, this has happened before, either on this aircraft or other similar aircraft. Similar errors have happened before. So, for example, if you're dealing with a data entry task, there may not have been a data entry error recorded on this piece of equipment, but we know that people make data entry errors reasonably frequently in terms of aircraft probabilities, reasonably frequently. So bearing in mind that the kind of reliabilities that you expect of aircraft components are sort of, well, anywhere between 10 to the -3 and 10 to the -9. Human errors happen more than that. So similar errors have happened before, or professional maintenance engineers believe it could happen. And again, before a workshop, design engineers will say, "Oh my Lord, they could say anything. We're going to be stuck with a list as long as your arm." That's not the case. Actually, experience would show that professional maintenance engineers are very conservative about what they believe another maintenance engineer could do in terms of error. And we more often find ourselves saying, I know you say it couldn't happen, but here's an accident where it happened. And people will be surprised by that. So I don't think it's anything that should scare us off, if you like. So now we have a human hazard analysis standardized approach for airframe designers, published by Heli Offshore. And we've also been presenting training in human factors for design engineers, specifically on the partly general human factors for design engineers, but also specific training on the human hazard analysis technique. What next? I'd like to think the general principles will become embedded in normal engineer thinking. I'd like to see human hazard analysis applied more widely. We're certainly going to be talking to the engine manufacturers soon, but I think it could also be applied to production. Some of the airlines have said, well, couldn't you apply this to errors that happen in the hangar? Well, we'd have to develop it a bit, but certainly something could be done there. And hopefully one day the system safety assessment will fully incorporate human error, but I think we're a little bit of a ways off that so far. So that's it. That's all from me. Happy to take any questions, thoughts.
So Hazel, thank you ever so much, and really appreciate it. Very informative, very insightful, it's what fascinates me is that these things don't happen over a few years, is it? I mean, it's just almost maybe not the entire career, but at least sometimes 10, 20 years that it starts, initiatives, and then there's maybe one example of it being applied, and then you try to take it to the next step, and then it evolves. If any of you have any comments to make, want to join the discussion, please put your hand up, and then I'll try to moderate this discussion. So do most of you agree that there is a kind of an issue that maintainers are not always able to follow procedures for a variety of reasons, not necessarily because they don't want to? Do you have a view, Hazel? I mean, this has been talked about for so long, isn't it?
One of the best things about running these workshops is that when you get the design engineers and the maintenance engineers together, they both really said they learned so much from doing that. The designers learn about the real life way things are maintained rather than what they, you know, workers imagined rather than workers done.
Yeah.
And the maintenance engineers get to find out why they're asked to do things a certain way and the consequences of not doing that, which they don't always know. So it's a very valuable kind of meeting of minds.
I'd be curious to hear your thoughts and also your views about particularly how can we really achieve that? And one of the reasons that I was just writing these questions earlier on this morning, and I reflected on my own experience. A few months ago, I went to a very large airline for an IOSA audit. And during the discussions, they said to me, well, we had a recent maintenance error. And then they said, look, you know, we've got the just culture and all the good process policy, everything else. And so we're not going to, you know, blame him or her immediately, and we're just going to put ourselves in his or her shoes and literally you know, try to understand why it made sense, because there was some issues about not following everything in the mate's manual. And literally, you know, it was a typical scenario, 3 o'clock in the morning, pouring down with rain and everything else. And then they said, look, here's the step-by-step instructions in the AMM. He didn't have to do the first one. He had to do the next 5, and then he didn't have to do the next 3, and then he had to do the next 10. So unfortunately, even the management started sort of empathizing with the individual. So, and I think for that reason, I kind of empathize with, in some cases, the technical authors. But saying technical authors and designers, I believe some of you on the call are also working in tech services. Actually, that means for me that working in an airline or CAMO organization, continuing awareness management organization, or within the airline engineering department, you are the technical author because you are developing some certain, you know, engineering orders and things like that. So interesting comments, some of them. I think there are a number of factors also, but the safe product remains an important factor for CRS staff, absolutely. And they sometimes have to take that ultimate final decision. The standard of training is designed to support engineering judgment. I think that judgment, sometimes people nowadays, lots of technologies and trying to automate things, even inspections by writing algorithms and so on. But I think we are not in a position to take the human out. Hazel, I'm sorry that once I start talking, I don't stop, but please do chip in. I mean, do you have any thoughts on some of the things that I'm saying? And please do challenge as well.
Well, one thing that I think could be a little bit clearer in manuals is, in order to get over this issue that you can't, you know, deal with every single scenario, but what you maybe can do is to make clear what it is that's important about this job. So, you know, whatever else, make sure that this is right. It could be a little bit more emphasized, but it's not always so easy. You know, some of the tasks are very complex. Yeah.
I mean, certainly, I was just working on earlier on with a couple of our students actually who's going to be doing some data collection next week. We've got a team from Boeing apprentices coming and working on our ground aircraft at 737. And it's literally, we developed an experiment by using a wearable tablet and presenting the maintenance instructions to the maintainer, not by pen and paper or even on a tablet, because he or she's going to be hands-free and actually voice controlling the instructions in front of his or her eyes. But as we were going through the maintenance manual, in some of the stuff that I worked on aircraft a number of years, and some of the stuff I'm looking at, and the student has no background, but he's asking me, what does this mean exactly? And we're looking at the same thing real time on the aircraft, and none of us can make sense. But I'm absolutely sure it made perfect sense to the technical author when he or she has written it, at the time. But that's the reality, and I think that reflects on. So interesting comments here. We can certainly share these, as part of maybe the output from this event. One writing instructor never did doing it, and I think that sometimes maybe need the technical authors and the planners, just like a CRM exercise. In the operational world, they bring pilot community and air traffic community together. And maybe sometimes, and that's what Hazel has been doing with these workshops, and bring the designer and the maintainer together so that they can talk to each other. As an airline tech services, we are often limited by regulations, true. Even if we identify areas instructions where it can be improved, we have to jump through hoops to make amendments. Jackie, I think I heard comments from some senior people, even MRO CEO level, and in some cases, yeah, it is 145 responsibility and requirement to report inaccuracies, ambiguities in the maintenance instructions back to the type certificate holder. And sometimes they do say that they're a bit frustrated the time it takes for things to happen. But I think we should pursue, we should persevere. We shouldn't just give up, but I take your point. I think that comment Hazel made about the design engineers meeting maintenance has many parallels with authoring engineers publishing it. Exactly, that's the point that I was making. I think even within the airline environment, that there are some maybe, dare I say, what Hazel's methodology can be applied, right? If you go within an airline, very large airline, they have their own engineering department, tech services department, and inevitably they do produce maintenance instructions and procedures for maintainers to follow. And maybe that's another way of looking at it. I don't know if you have a view on that, Hazel, because I think, as well as, AMMs, IPCs, these are coming from type certificate holder, but airlines, camos actually produce these nowadays.
Yeah, so I've just responded on the chat through Heli Offshore again. Simon and I are running a workshop in September or October for tech pubs. So we're bringing together the technical pubs people from the design organisation alongside the people writing the instructions in the maintenance organisation. So that should be interesting. It'll be the first time we've done it, but we're really looking at human factors of instructions, if you like.
Yes.
And trying to firstly, again, get some improvement there, but also bringing them together with, well, this, we've identified this as a really sensitive task. So let's look at the flow from the design engineer to the person writing the OEM's procedures, to the person writing the local procedures, to the maintenance engineer, and, and try and make this as good as possible, because this is a task that matters a lot.
Yeah.
I just mention there's a kind of another aspect to this where the technology that is providing the instructions on site. I was talking to some people from a particular helicopter operator who said, yeah, well, our company is so security conscious that when we're trying to do a task that requires maybe a number of different documents we have to reference, that every one of those documented systems has a different password, and every one of those passwords expires after 10 minutes, and every one of those passwords has to be changed every month. Right?
Almost just saying don't follow them.
But not on the same day. So can you imagine you're trying to hold this complex information together, and you just reference it to this one, that's closed down again, can't remember the password. So there's a kind of element in there that none of us have got control over, but that can play quite a significant part, I think.
Yeah, I mean, that's a very fascinating thing that I think that sometimes it's trade-offs between different requirements, whether it's security, environmental. I think sometimes nowadays even environmental requirements or legislation or regulations sometimes have an impact on how people behave, because you're trying to achieve sometimes competing goals. But one thing that also brought my attention is it's Dave's comment about it would be ideal if aircraft can proactively collect feedback from mate's engineer and make any necessary changes on mate's instructions as well as future products. And I mean, that's a very interesting concept. What made me think is, for example, this wearable tablet that we trialing, and there are lots of things out there, but I'm not going to try to sort of do a sales pitch, but basically it has the opportunity to even record things. And we're even considering, as part of while people are carrying out the jobs, particularly in safety, the critical steps within the process, that they can actually record things, how they're doing it. And also even as evidence that if they correctly install the O-ring or whatever, then actually they've got record of it and it's all automatically uploaded to the server. But then, of course, there's all kinds of other complications about cultural issues, the acceptance, and whether you want to wear a body camera, just like police do nowadays, some countries. So it would be fantastic, wouldn't it, that the manufacturers would have a much better idea of how people are behaving when they're doing some of the safety critical tasks. But I think not straightforward, but maybe this needs to be considered. Any other thoughts before we close about what do you think that the industry should focus on in terms of airworthiness risks? Hazel, if I may put you on spot.
Other things that they should focus on in airworthiness risks. Making sure that I was going to say, making sure that the training and the design complexity are matched up.
Yes, yeah, that's an interesting one, isn't it, in relation to this? Yes, yeah. Sorry, somebody else was joining us.
Hi, Cengiz. Yeah, it's Trevor Woods here. Since you mentioned my name, I thought I would
absolutely
show my voice. Yeah, I'm very interested in the comments on complexity and technology, because I think we see the level of automation increasing a lot at the moment. And I wonder if Hazel's got any thoughts on, will that change her approach to the human centered hazard assessment? Because I think this will be a big thing. I mean, we've seen human related issues before related to automation, and it's we're going to have more and more automation as we go.
Yeah, I mean, there's a lot of difference between the kind of simple error, if you like, of a thing that's done binary incorrectly, and things that are just too damn difficult. And when we learn something and then don't use it for ages, like how to interpret particular kinds of failure or what to do in particular situations, it may be 10 years before you actually have to apply some of the things that you learned, which it's like being suddenly jumped on to sit A-level maths again. It's just like, yeah, I remember knowing it, but I've now got 3 seconds to interpret this and do something to sort it out. So I think there's something around what expectations we're putting on people in terms of what they're going to know and remember and then use to come to a certain conclusion, and how much time are we giving them to do that. Time was when every pilot had experienced a couple of engine failures. But now you may not have an engine failure in your lifetime, in your professional career. So when it happens, it's kind of a surprise. So have we adapted the training to the level of complexity change, and what are we actually expecting from people in terms of knowing what to do and figuring it out in the time available. I mean, the A380 that had a problem and survived it happily had something like 78 alerts. Come off it. How can you expect someone to be working their way through that when they're in a safety critical situation? You know, so I think it's all a question of, as engineers, we all get fascinated, don't we, by what we can do, but I think we just have to think a bit about what are we actually expecting of a person who isn't eating, sleeping, breathing this system as we have been in designing it, but is out there using it, and this is just one of the tools in their toolbox that they probably haven't seen for how many years, and they're going to be expected to respond. So I think we have to start thinking about complexity from the eyes of the person who's going to be in the situation, really.
It's fascinating. I mean, the Claire's comment on the chat line is there a case for promoting concept of overlearning for critical tasks? I think, you know, if we look at these things, I think the Hazel's methodology is also clearly trying to achieve that. Sort of, we're not going to try to do everything. And same thing about improving procedures, improving the instructions. No one has the resource to do that, because we can make the IT people rich but not achieve the outcome that we're trying to achieve. And I think for me, that in fact, I asked students to write an assignment on this. For me, I think the complexity is one thing, simple tasks versus complex tasks. And secondly, task familiarity. Even if the most complex task you've done, you need to do, if you've done it once, and I think certainly an element, I'm not saying completely, you know, you've got to do it from memory again, but certainly task familiarity is something to be considered of. If someone's doing the first thing and a complex task, it's almost like sort of, you know, just you've got to make sure that it's well-designed procedure, instructions, and actually is followed to the letter.
There's also the issue of, you know, someone said, we do practice these, you know, critical tasks massively. Every pilot's done an engine failure at V1 how many times, but how often do we practice, for example, I don't know, a go around from a high level?
Yes. Yeah.
You know, the other things that are safety critical that aren't on our safety critical practice list. Yeah.
And of course, then we get caught. Like, no one was talking about high altitude stalls and things like that until Air 447, and maybe some people were talking, but it certainly wasn't the higher in the agenda. Yeah, it's and the very last point, if I may, just on this Paul Ev comment, effect of prolonged parking on airworthiness on an aircraft, even manufacturers may not fully understand. And that's a big challenge. And I was representing IFA, part of the various working groups within EASA when we first started, even at the beginning of the pandemic, to identify its COVID-19 safety risk portfolio. And this was certainly one of the top agenda items. But certainly my personal view on this particular one is about basically, you know, there is a methodology, what we all know, MSG3, how to develop maintenance tasks for utilized aircraft. But I don't think there's a similar methodology that how we would actually develop maintenance tasks based on what logic, what kind of assessment for prolonged parking. And I think that's why I kind of bagged on the drum a bit, but it didn't get anywhere. But I'm curious. I'm curious to how manufacturers, of course, they came up with a lot of advice, a lot of different tasks and recommended tasks and so on. But I think maybe we do need to think about, because, you know, there's still a lot of aircraft parked out there, and sometimes long-term, and inevitably some of them are going to come back, return to service. And we all know that we already had some issues, and even airworthiness directives issued. So we'll keep you posted about future events. And once again, thanks everyone. And I'd like to hand over to Frank for maybe last few words, if you like.
Yep. Cengiz, thank you very much indeed. Hazel, you've done a great job. It's a very, very complex subject. I've sat here listening and thinking of some of my experiences over the years. And also that one of the challenges that I faced when I was in Rolls-Royce, running the Rolls-Royce commercial engine business, because of the way that the company was structured, the designers felt they were the top of the pile. The manufacturers felt they were a bit further down the pile, and the maintenance guys were even further down the pile. And one of the things that we started to do before I left was to make sure that no design was signed off by the manufacturing organization or the maintenance organization before it was published. In other words, before it became a design. And it was amazing that the bond that built up between the design teams, the maintenance teams, and the manufacturing teams. It was really very, very good. It's not a perfect solution, as you say, but to get people to talk about the risks at the design stage and to carry that through to the complexity of the maintenance makes a heck of a difference at the end of the day. And I don't know what it's quite like in Rolls-Royce today, but I doubt if they've dropped that, because it was so successful. It really was. But your presentation covered most of that area anyway, except you didn't say too much about design. Thank you very much, Hazel. That was an excellent start to our online seminars, and we look forward to relating to you as an ongoing thing. So we'd like you to drop in on some of our seminars, and that would be very good for all of us.
Thank you.
Certainly, I think it's okay with you, Hazel, if we just finalize this recording and actually make it available publicly.
Sure.
Spread the word around, and I think what I'm certainly going to have that conversation with any airline that I will visit in the future, because I think there is a place for even the airline itself to consider, because they themselves are not only taking it from the manufacturer and actually sending it to the hangar. It's actually the airline camos are producing procedures and instructions and various other aspects. Some of it's coming from the OEM, but so some of it sometimes they develop it from scratch. And of course, that sort of the documentation is maybe only one aspect, but certainly an important part. Thank you so much for all your interest. Thank you for attending, and we hope to see you in the next IFA webinar.